We have already learned how to write the Lewis structures for different molecules and ions. For certain molecules and ions, more than one Lewis structure is possible. For example, consider the following possible Lewis structures for an ozone molecule. These are the two structures possible. In both the structures, one oxygen-oxygen single bond and one oxygen-oxygen double bond is present. These two structures imply that one bond is shorter than the other. The normal bond lengths of oxygen-oxygen single bond and one oxygen-oxygen double bond are 148 picometers and 121 picometers respectively. But experimentally, it is determined that the bond length between any two oxygen atoms in ozone molecule is the same, which is equal to 128 picometers. This implies that the bond length between the oxygen atoms in ozone molecule is intermediate between oxygen-oxygen single bond and oxygen-oxygen double bond. It means that all the bonds in ozone molecule are equivalent. Therefore, neither structure 1 nor structure 2 explains the observed bond length. It is observed that for certain molecules, one Lewis structure cannot explain all the observed parameters such as bond length, bond strength, and so on. Therefore, more than one Lewis structure is required to explain all the observed parameters, as a single Lewis structure is inadequate to represent the molecule accurately. If a molecule that can be represented by two or more structures which differ only in the arrangement of electrons, then the molecule is said to be in resonance, and the set of several possible structures are called resonance structures or canonical structures or canonical forms. Any two resonating structures are represented by inserting a double-headed arrow between them. It is important to note that there is no equilibrium between the canonical forms. All the canonical structures have similar energy and the same arrangement of atomic nuclei, but differ in the arrangement of electrons. However, the molecule never actually has the structure of any of the canonical forms at any point of time. The actual structure of a molecule is a hybrid of all resonance structures possible. It is called a resonance hybrid. This resonance hybrid is more stable than any of the contributing resonating structures. In this example, the resultant of these two structures, that is, the resonance hybrid, explains the equivalent nature of the bonds and the observed bond length, which is 128 picometers as shown here. Let us reinforce this concept by considering the possible Lewis structures of a carbon dioxide molecule and polyatomic nitrate ion respectively. We can represent a carbon dioxide molecule by the three following Lewis structures. None of the single structures explain the observed carbon to oxygen bond length, which is 115 picometers. The magnitude of this bond length is found to be intermediate between the bond lengths of a normal carbon to oxygen double bond, which is 121 picometers, and carbon to oxygen triple bond, which is 110 picometers. Hence, the resonance hybrid of these structures, as shown here, explains the experimentally determined bond length. Similarly, we can represent the nitrate ion by the three following Lewis structures. In each structure, there is one nitrogen-oxygen double bond and two nitrogen-oxygen single bonds. However, experimental studies reveal that all nitrogen and oxygen bonds are found to be equivalent. Hence, the resonance hybrid of these three structures depicts the equivalent nature of nitrogen-oxygen bonds. Therefore, the nitrate ion is best described as a resonance hybrid of the three possible canonical forms as shown here. Thus, we can conclude that resonance stabilizes the molecule as the energy of the resonance hybrid is less than any of the canonical structures. Also, a molecule can have only a single structure, that is, the resonance hybrid of all the canonical forms.